Hello, everyone. Welcome back. So today will be our last class meeting for the divide and conquer algorithms. Okay, so we're gonna look at another example, and I think it's a really cool example of applying the divide and conquer thought to a problem that is nowadays so often seen, and it's a very basic application to the machine learning based AI techniques that we are using basically every day. Okay, so the problem is called a matrix multiplication problem. Okay, so we're gonna, when we analyze this such a algorithm, such a divide and conquer algorithm for solving this problem, we're gonna use the master method that we introduced in the previous lecture. So let's just give a short review of the master theorem or master method. Okay, so basically you need to consider three conditions. Given a recurrence like this, right, we just need to look at what is A and what is B here, and also the function f of n. So we need to make a comparison with two parts. The first part is a polynomial function, okay, n raised to the power of logarithm base b of a. So that is one function, and the other end of the equation is f of n. So basically compare these two functions, and whichever that grows faster basically dominates the running time, dominates the final solution here. So there are basically three conditions. And the special case is the second condition, that when the two have the equivalent growing speed, then the solution is either one times the logarithm term. Okay, and also the technicality about the epsilon means that we need to find that either one is polynomially greater than the other one in terms of growing speed. Yeah. So it's a very it provides a very quick solution to basically any kinds of equations that looks like this form. Okay, so let's look at the very specific problem that we are interested in today. Okay. Slides. I'll just quit. Okay. All right. Go to the slides where we begin today. All right. Okay, so it's a matrix multiplication problem. So from the name, we know that it's has to related to the linear algebra. Okay, so let's look at the problem, and basically it's the multiplication between two matrices that we are concerned here. And assume that we have two matrices, and we made some simplification. So it's not they are not matrices of random sizes, of random shapes. They are all square matrices, which means the number of rows and equals the number of columns. So in that way, we can call them the n by n matrices. So the first n is the number of rows, and the second column is the second value is the number of columns. All right. So when we indicate the elements, so whenever we have a matrices, we can write them down like this, right? So if this is the capital A, then if we want to write all the elements in that matrices, we can use something like A11, and this A is in lowercase. This small a is the elements in that matrix. So that is A11. So the first one means it's the first row. The second one means it's the first column. So we can know that the second elements in the first row is A12 and A13 until the last column, which is A1n, right? And the second row starts from A21, the A22, and the A23 until A2n, right? So that's the naming conventions for all the elements in that matrix. So each element has a index, has a pair of indices, which is I and J, indicates the row index and the column index. Okay, and use this pair of numbers, we can basically locate any elements in that matrix. Okay, so what we are interested here is the product between A and B here, capital A times capital B. And since A and B, they are not simple numbers, they are matrices. So let's review the process of matrix production a little bit. We basically need to first align the two matrices together, right? A times B, which is the result of placing two elements here. That is our A, and that is our B to the left, to the right of A. Okay. So what we need to do to multiply these two matrices is that we will first look at the first row of A. That is from A11 to A1n, right? And also we need to look at the first column of B. Okay, so the first column, the first element is B11 and B21, right? And B31 until Bn1, right? So we take the first column of B and we need to compute the dot product between the first column of A and the first column of B. Okay, between these two vectors. Okay, and the result is what we called C11. Okay, and we need to put that C11 into the first elements of the resulting matrices, of the resulting matrix. Okay, so the shape of the results of the matrix multiplication is determined by the two matrices being multiplied, because we know A is n by n and B is also n by n. So the output size, the results matrix is in the same dimension, is in the same shape, which is n by n. Okay, so how we need to compute C11 is the taking the dot product between the first row and the first column, and we can do this for all the elements left in the results. So C12 is the dot product between the second column of B and the first column of A, right? So this is something we need to have a little bit review here. Okay, so the nature of dot product. Okay, so if we want to do all the reviews, we will need to trace back to the definition of vectors and the definition of dot product. So we're gonna basically skip that step. And if you have problems, if you have need to have some review about what dot product is, I will recommend you to simply Google it and try to find any references in linear algebra textbooks or online materials. It's everywhere, I think. All right, so the form of dot products between two vectors can be written as the summation of a series of products here. Excuse me. So if we look at this formula, the first number a ik is the elements at the ith row and the kth column at matrix A. The bkj is the kth column, is the kth row and the jth column in matrix B. So when we use these elements times these elements and iterate over all possible k's and sum up all the products, that'll be the results for Cij. Okay. All right. Then let's think about how complex the problem should be, or the solutions should be. And it's quite straightforward, right? We know that the outcome is a matrix, and we know its size. We know its shape. It's a n by n matrix that has n square entries or n square elements that need to be computed. So, and in order to compute each element, we need to do this summation of n values. Okay, so intuitively, it's a lot of computation in order to compute the matrix product, matrix multiplication. All right, and let's look at some very direct implementation of this matrix multiplication. So we define a square matrix multiplication procedure here, and we didn't use anything fancy because we just take the two matrices to be multiplied as inputs, right? We record the number of rows, and we, in the line 2, we allocate some memories, some space from memory to store the results. All right, and within the main body of this code, we can see it's a triple for loops, right? Within the most outer for loop iterates, use the loop counter I to iterate from 1 to n. The second layer, it's another for loop that use j to iterate over 1 to n, right? And within the body of the second for loop, we use a Cij, okay? Because the I and j are used to go through all possible positions within the output matrix, right? So Cij is the element we want to compute. And at the beginning, we don't know what it is, so we initialized it to 0, okay? So according to the equation here, Cij is the result of sum up a bunch of products. So we need to use a third for loop, okay, to implement this sigma operation, right? The sigma operation is the summation of a series. So any kind of series in the need to eventually be implemented using some loop structure, right? So we basically use a third for loop to do this sigma, this summation over k, okay? And it's a cumulative summation. So Cij will be updated after we have added to the product here. Okay, so this implementation actually is a very reasonable solution, right? It seems like this is everything. It includes all we need to do, okay? And it seems that there's no way to do the any further improvements. It looks like basically we need to compute all these triple for loops. Okay, seems inevitable. Okay, so as we can infer from the triple for loops, right? Because each for loop needs to go through n iterations, and that in total counts as n to the power of 3 or n cubed. Okay, and we know this is a really inefficient solution, right? We already know that the n square, right? Even if when it's n squared, it's already not that efficient. Not to mention n to the power of 3. Okay, so this is really something that we wish to have a better solution on. Right? So we will think about the problem from a divide and conquer angle. Okay, let's see whether such a problem of multiplying two big matrices, two big chunk of matrices, and into some smaller sub problems. Okay, and that is doable if you really think about the composition of matrices. It's just a bulk of numbers, right? Consist of several rows, and of course these rows can be splitted, and those columns can also be splitted, right? So if we, it's pretty approachable if we want to divide the subproblem, if we want to divide the original problems into smaller ones, right? So we take some, as we usually did, we take some simplified assumption. We assume that by assuming that the shape of those matrices, the size of the matrices are exactly the power of 2, so that they can be easily divided. Okay, this is a trick that we mentioned when we divide the input sequence when we talk about merge sort, right? So with this assumption, we can divide the n by n input matrices into 4 submatrices, and each submatrix is in the shape of n/2 by n/2. That's what we did. So what we did is to place a cut horizontally and vertically to divide the matrix into 4 submatrices. Okay, and the resulting submatrices are something we can denote use the similar notation. We still use the capital A, but now we give it a sub-index, a subscript, this 1, 1. So this 1, 1 is not to indicate that this is the first, this is the elements at the first row or first column. No, it is not like the elements indices. It's the indices for the sub matrices. So it's in the first, so it means this is the sub matrices at the upper left column, at the upper left corner. Okay, so the second sub matrix has the subscript 1, 2, so as to A 2, 1 and A 2, 2. So we did this for B and C. All right, and C is where we store our results. So given this division, we can rewrite the equation C equals A times B using some knowledge from linear algebra. Okay, right? We rewrite it into the form of submatrices, and it actually indicates we need to follow the same rule as matrix multiplication, right? So if you look at the first chunk, this upper left chunk within the result, C11, how do we compute C11 is very similar to the way we compute the first element in C, right? We need to take the first row in A. This time we have 2 submatrices, and the first column of B, which is also 2 submatrices, and then compute the dot product between these 2 sub areas. Okay, and the dot product is A11 times B11 plus A12 times B21. Okay, so if we look at this purely from the form of the equations, it's very similar to the one that we used for computing the small C11, right? So it's just some decomposition trick from linear algebra. Okay, and we can do this for basically C12, which is also in the form of this dot product. and C21 and C22. Okay, so now looks like we have a series of subproblems. Right? Can you notice that? So here, this is this multiplication between A11, B11 is the subproblem that we need to solve, right? And this is another subproblem. All right, third one, fourth one, fifth one, sixth one, seventh one, and the eighth one, right? So we kind of basically convert this original problem, the multiplication between A and B, into that many, into 8 subproblems, right? We can basically use this divide and conquer, use this based on the results of this division to write some divide and conquer algorithms, right? Use a recursive style, right? Because those smaller problems, the multiplication between A11 and B11, it's just a smaller instance of the original problem, right? We can write a recursive algorithm quite easily, given this decomposition. All right, let's directly give the solution. Look at the solution. Okay, the procedure that we write here is called square matrix multiply recursive, right? The same inputs A and B, same initialization, and now because it's a recursive solution, we need to recognize the base case or the boundary case, where if the input only has one number, right, then that means we cannot divide this basic case any further. So we will simply return the results, right, by computing C11 as the product between the two numbers, okay, because there's only one number in each matrix. If it's the other case, that means it's the recursive case, then we need to divide the problems, divide the matrices, use the way we shown in the previous slide, right? So this line 5 says we need to partition A and B and C into 4 regions, okay? So that we can have the capital A11, capital A12, capital A21, and capital A22. So we get the solutions for each sub-region into sub-chunk within C using the formula that we defined in the previous slide. Okay, so you can notice that here the multiplication between A11 and the B22 is obtained by this recursive call, right? It's a call to the function itself, right? Because we are solving the same kind of problems with smaller sizes, okay? So there's a second recursive call, third recursive call, fourth, until we have all the 8 recursive calls are invoked, okay? We basically need to solve all these 8 recursive calls. And as the results, we will finally return the C after all the recursive calls are done, okay? So all these recursive calls will invoke further recursive calls if the problems are divisible. All right. So this is quite a clear divide and conquer approach, right? So there's a technical detail about how to partition the matrices. So this is important because this is important when we want to analyze the running time of this divide and conquer algorithm, right? Because we need to estimate how much time it's going to cost us if we wish to divide the matrices. So those divide matrices operations do not come with no cost. They all have some additional computation come along. Okay, so think about it. Because we need to divide 3 matrices and each one into 4 submatrices, we need to create 12 in total new matrices. Okay, what we need to do is to copy all the elements from the original place, right, into the new submatrices. So if we are going to create some submatrices in some new memory space, so that is our assumption. But that's gonna cost us considerable amount of time, right? So think about the problem. In order to copy one matrix to another place, we need to use two for loops to go through all the elements in that source matrix and copy each element to the target matrix, right? That is not a free operation. So if we use some smarter way to avoid this, say, if we use some index calculation trick, right, to represent a submatrix by a range of row and column indices within the original matrix, that'll save us this additional time. Okay, so we can assume that with this smart index calculation trick, and the details we are not going to go into the details here, but all we need to know that with some implementations, we can reduce the cost for this dividing step into constant amount of time. Okay, which is good news for us. All right, and if we go ahead and analyze the total running time for the problem. Say, in the base case, right, we just need to perform one multiplication, which is obviously a constant amount of time, right? And the real cost is in the recursive cost here, right? In the divide and conquer step. So in this conquer step, we can write the solution, use the recurrence form. Okay? If we use capital T of n to indicate the solution to the original problem, then of course, because our input is now half the size of the original matrix, then we can use T of n over 2 to denote the cost for this first subproblem, right? And we have a second problem, which is another T of n over 2. So that is 2 times T of n over 2. That is the cost for computing capital C11, right? Because C11 is the summation of 2 subproblems. And also for C12, C21, C22. That in total should be 8 times n over 2, right? Since there's some additional summation or addition here, when we sum up 2 matrices, right, those summation matrices are not free, right? When we are adding 2 matrices, we need to go through each element in the 2 matrices, right, and sum up the numbers at the corresponding positions. Okay, so that had the cost for big theta of n squared, because we need to use for loops to go through all the matrices. All right, so that gives us a solution to solving all the subproblems. Then it's time to take everything together, right? The total running time should be the summation of these components. This is the partition step, the recursive calls, and the summation within the recursive calls. And that should comes into this final form, which is a times t of n over 2 plus big theta of n squared. I think it's this is the form of the first question in assignment 2 that we need to solve, right? So, but in assignment 2, we want to use the substitution method to solve that. But right now, given this form, we know that we can use the master theorem, right? By observing what is the A and what is the B, right? So it's a quite straightforward solution. When A equals 8, the logarithm of base 2 of 8 is 3. And this resulting n to the power of 3 is obviously at a higher order compared to the big theta of n squared here. So we have a higher order term, which means the solution is determined by this higher order term, and we know the solution should be big theta of n to the power of 3, right? So that tells us that, which is not good news. It says the take-home message is that we have spending a lot of time implementing this divide and conquer algorithm in the hope to achieve some better performance than the brute force triple for loop implementation at the beginning, right? But we didn't achieve anything better because the running time is the same as the triple for loops, okay? And it's kind of frustrating, right? It seems there are no further ways to implement to get a better implementation, right? But actually, the divide and conquer recurrence can give us some ideas of where to improve the algorithm. If we look at the algorithm, we can see that what master theorem tells us is that the determinant term is this one, right? And this order, the order of this function, is determined by the 8 and 2, the two numbers here. So, is there any chance that we can make the constant A in this case a smaller number so that the recursion tree can be less bushy, can have less branches so that the algorithm can be further improved? So I see a comment that I question that the recursive method take more space than the for loop method. Yes, so the recursive call in a modern computer architecture is not needs to be optimized. So any recursive call is basically a consumption of the stack space. So we push the head of the function, we push the address of the recursive call into the stack. So a lot of recursive call in this case, particularly in this case, we have 8 recursive call. That is a huge amount of computation, consumption for the stack space. So that is correct. The recursive call is not better. It could be worse than the triple for loop implementation. Okay, so following this slide, following the idea that we want to kind of have some smaller a's instead of this constant a here. That seems to point us a direction to further optimize the solution. All right, so we'll look at what's it called a Strassen's algorithm. Okay, so the idea of this algorithm is that instead of computing 8 recursive call, instead of calling 8 recursive multiplication computation, we can now only perform 7. Okay, that's already a improvement, right? Because we lower the number, constant number. So the trick is that we need to conduct some additional addition operations between the sub matrices. Okay, and the solution is not straightforward if we look at it at once. Okay, but it turns out that all the jigsaws puzzle pieces will place together, and we're gonna go through this to see how the tricks happen here. Okay, so we basically need to conduct 4 steps. All right, the first one is the same thing in the divide and conquer, in the straightforward divide and conquer approach. That is to split all the to divide all the matrices. And the second step is something new. It creates some intermediate matrices, actually 10 of them, from S1 to S10. Okay, and each of these intermediate matrix is also a half of n by half of n, and it's actually the summation or difference of the 2 matrices created in the step 1. Okay, I think yes. So because we know that the summation or difference between 2 submatrices will cost n square amount of time. So that is something we can take a note here, and we will use it to express the total cost later. And the third step is also an intermediate step. It will use the capital S matrices computed in step 2 to recursively compute 7 matrix products, which is P1 to P7. Okay, so this is actually where the improvement happens, because we don't compute 8 subproblems. We're just computing 7 matrices, 7 matrix multiplication problems. So, and these subproblems are solved recursively. Okay, so now it's not 8 but 7. We can see where this is where the improvement occurs. Improvement happens. Okay, and lastly, because we don't have the C's yet, we will use the P's computed from step 3 to conduct some additional adding and subtracting combinations in order to compute the final capital C matrices, C11, C12, C21, C22, which also comes with some additional n square amount of time. Okay, so it has some additional cost here, but we will see that it turns out that the total recurrences can be indeed improved. And in the next few slides, we're going to see why this approach works. Okay, so let's first look at the recurrences. Okay, so in the base case, it's just the same as the direct divide and conquer approach, which is just a one scalar number multiplication. And for for larger cases, if we combine all the step 1, 2, and 4, they will together take big theta of n squared time. Okay, and step 3 performs 7 multiplications that requires additional, that requires a recursive cost. So we can basically write the recurrence into this form, which reduce the number 8 into 7 here. And it's obviously an improvement, because if we compute the master theorem, use the master theorem to compute this polynomial function, it's n to the power not 2, 3, but to a logarithm 2 of 7. And this quantity, log 2 of 7, is slower, is smaller than 3. So which means the total function, the new solution here grows slower than the cubic function. Okay, so the difference may be small, but it will be very significant improvement if we have very large matrix to be multiplied. Okay, so nowadays in the modern machine learning applications, we have matrix multiplications everywhere. Whenever we want to compute the matrices, any kind of this Strassen algorithm, the performance improvement provided by the Strassen algorithm is quite significant when we have large n's. Okay, all right, let's jump into the details. So step 1 is no different from the old way. Step 2, remember, we need to compute some intermediate matrices, which are capital S matrices, right? We have 10 intermediate matrices from S1 to S10. So the computations that need to compute it is here. That the equations are listed here. Okay, it seems not regular at all, right? Unregular. It's just some random patterns. So that doesn't matter. We'll see how the pictures can be put together. Anyway, it's in total 10 adding or subtraction between 2 submatrices, and that will take big theta of n squared amount of time. Okay, and then the step 3, right, which is a recursive call, which is 7 recursive calls to compute P1 to P7, right? So P1 is A11 times S1. Okay, since S1 is the B12 minus B22, right? So the meaning of A1 times S1 is A11 times B12 minus A11 times B22. But this is not what we will actually compute. What we are actually compute is this A11 times S1, recursively solved by the algorithm itself. Okay, we're not going to expand the equations. Okay, these are the actual computations we actually need to compute. Okay, these are on the left within the yellow dashed line box is just the meanings of the what the results or what the results equal to. Okay, it's just to show how the products equal in terms of the original submatrices created in step 1. Okay, so within this yellow region, there's nothing as S1 or P1, right? It's just the original. It just consists of the original submatrices. All right, and next, the step 4. It's the final step to add or subtract the matrices, the P matrices created in the previous step in order to compute C11, C12, and so on. Okay, so for C11, it is the result of P5 plus P4 minus P2 plus P6. If we copy the equations from the previous slide to this slide, okay, let's go to the previous slide again. So P5 is this very long term, right? So if we copy P5 and the other P's to the next slide, we will find that it looks like this. That is P5. P5 is like this. And P4 is the results of negative A22 times B11 plus A22 times B21. And P2 is the third line. P6 is the last line. So anyway, when we put these equations together, we can see that a lot of eliminations occurs, right? So let's use the same color. So if we align the equations, we will find that, okay, these two eliminates. These two eliminates. And these two, right? These two. All these terms eliminates. And the only term that's left are the A11 times B11 plus A12 times B21. Okay. And that is exactly the definition of C11. Okay. Which means the equation here is a correct computation. Right? If the results doesn't equal these two equations, then we're wrong, right? But the trick is here that we actually are correct because all the terms in the middle, they eliminate each other. Okay, so it's a really amazing solution, right? So C11 can be correctly computed, and we can go to C12, which is also the combination between the intermediate P's. Okay, so if we place P together, then the first two, the middle two terms eliminates, and we can have A11 times B12 plus A12 times B22. That is also exactly how C12 needs to be computed, right? And C21. Also, we have some elimination and having this valid equation for computing C21. And C22, lastly, is a little bit longer, similar to C11. Also, we have a lot of equations eliminated, terms eliminated, and we would finally have the correct form of how C22 needs to be computed. Okay? So, putting this all together, we know that the C11 to C22 can be correctly computed, right? And we have the solutions solved. And let's go back to the, yeah, this is kind of crazy because this is not straightforward at all. So let's go back to the equation, yeah, to the recurrence equations. Indeed, we can improve the solutions to 7, lower the constant from 8 to 7. Okay. So it's a really, I think it's a really amazing achievement. And it's not, well, it's not a perfect solution that doesn't comes with some side effect, like because there are some way more additional subtraction and addition operations, which means the numeric stability of the computation might not be that high as the straightforward triple for loops or straightforward straightforward divide and conquer computation. And also the constant factor is very high, which means when n is not that big, the improvements may not be as significant. Okay, but as I said, usually in a modern high performance computing case, like machine learning, AI based computations, we need to compute a lot of matrix multiplications. So it's quite a significant improvement when we have a smaller numbers here. Okay, and Stratsen's algorithm That's the name of the inventor, I think. And it's actually nowadays we have we have some better solutions than this one. And on the Wikipedia page, you can find some information about that. And it's a way that people are trying to explore the optimization of algorithm of the matrix multiplication algorithms. But it seems that it's a quite a niche area, and nowadays we have very fast hardwares, and it seems that the solutions provided by this algorithm is already a very good one. Okay, yeah, but I haven't looked at the actual implementations in for example, common and numeric computing frameworks like NumPy, like backend C++ implementations. I'm not sure what kind of algorithms they use, but there must be some um, optimizations like this and tons of other details. Alrighty, so that's the last problem we introduced here for the divide and conquer approach. And I'm gonna stop video recording, and because we have some time left, we can actually go enters the next chapter, which is sorting algorithms. Okay, so yeah, let me stop the recording here.